Am I audible? Okay. So let's start. Hello everyone. My name is Srijay Mukherjee, and I will be taking this live session for NPTEL course on computer organization and architecture. I am a research scholar at the Department of Computer Science and Engineering, IIT Kharagpur. So, like all weeks, we will be discussing some sample problems in this live session, which will be asked mostly in your assignments and mostly in your assignments and like exam. So we will be covering today week seven's like the topics that has been discussed, that are adders, multipliers, etc. So let's start. So this is the first question. What is the decimal equivalent of 111 101 011? So what is the decimal equivalent of this number that has been represented as a 2 complement from? So you see this is a 2's complement number, and also one of the properties, the first digit is a 1. So 111 So if you notice, this first digit is 1, so that means this is a negative number. So this is a negative number. So uh, how to convert it directly into the decimal, these two's complement form? Whatever we have done in the course, it was mostly like converting it previously, that we have converted direct binary to decimal, but this is little bit different. So what we will do, so we will write this as we will write this as minus 1 into 2 to the power of 7 plus 1 into 2 to the power of 6 plus 1 into 2 to the power of 5 plus 0 into 2 to the power of 4 plus 1 into 2 to the power of 3 plus 0 into 2 to the power of 2 plus 1 into 2 to the power of 1 plus 1 into 2 to the power of 0. So as you see, but the only difference that you will find is the first number is considered as minus 1. The reason is it is a negative number. If it had been 0, then it will be 0. So the first digit will always be either -1 or 0, and the rest will be 1 or 0 that we have done previously in like while converting a normal to normal binary to decimal. So what will be the value? So this is minus 128 plus 64 plus 32 plus 0 plus 8 plus 0 plus 2 plus 1. So this will come down to minus 128 plus 96, 104, 106, 107 minus 21. So this is the answer. So basically this is a very shortcut way of converting a 2's complement number into a decimal equivalent. Okay. So if you have any doubt, you can ask. I will go to the next question. Okay, so let's go to the next one. So the question is the largest number that can be represented using a 8-bit ones complement representation. So if you have gone through the slides, you know the range of ones complement numbers are minus 2 to the power of n minus 1 minus 1 to 2 to the power of n minus 1 minus 1. So these are the numbers that can be represented using ones complement number, right? So what is the largest number that can be represented? That is this. And this one is the smallest. So uh, so for 8-bit it will be 2 to the power of 8 minus 1 minus 1, that is 2 to the power of 7 minus 1, that comes out to 127. So the answer is 127 is the largest number that can be represented using 8-bit ones complement representation. This is very basic, like the theory has already been taught in the class, and just you have to put the number and solve this. So let's go to the next one. So the question is, if we implement a half adder with basic gates and or not, how many basic gates will be required? So you have been given a half adder and you need to, if we implement a half adder, so how many basic gates will be required? That is and or not. So what is a half adder? A half adder is, for a half adder, A is equals to, in a half adder we have only two inputs. This is the sum of that is carried out using a half adder, and the carry is AB. So what is the sum? If we just convert it, is AB bar plus A bar B. So this is the sum and this is the carry. Now the question is, if we implement a half adder with only basic gates and or not, then how many basic gates will be required? So we have been given only and or and a not. So the question is, how many basic gate will be required in this case? So if we consider the in sum part, how many basic gates are required? We need a and operation. We need a not operation for B naught on A naught. So that is, you require two not. Then we require one. This is one add operator. This is one multiplication operator, and there it is another multiplication operator. So we require two AND operator, so for these AND operations, and we require only one OR operator for the add part, right? And if we go for the carry one, in carry we require only one AND operator, that is for AB. So what is the total gates required? Total gates required is 2 plus 2 plus 1 plus 1, that is 6. So the correct option is A. Clear? So if you have any doubt, you can ask. So this one is, if you have any doubt, you can ask now. I will respond to your doubts. Can you explain AB once? So AB is the carry generated, that is So if you want to know how this is happening, you need to understand the sorry, 1 minute. So you need to understand the truth table. So this is the sum. The sum, and this is the carry. So if you add 0 and 0, so what will be the sum? 0. And what will be the carry? 0. If we add 0 and 1, what will be the sum? 1. What will be the carry? 0. So if we add 1 and 0, what will be the sum? 1. What will be the carry? 0. Now if we add 1 and 1, what will be the sum? 1 plus 1, 1 plus 1 is generally 1, 0, but the sum in this case will be 0 and the carry will be 1. So if you know, if you want to represent digitally this carry, it will be AB. Okay, so let's go to the next question. So the question is, the delay of each basic gate is delta. Suppose the delay of each basic gate is delta and the inputs are available in both complemented and uncomplemented forms. Then the total delay required by a sum and carry output of a full adder is which of the following? This may sound a little complicated, but if you have completely gone through the lecture, so you will know what is the sum and what is the carry for a full adder. So what will be the procedure? I'm just giving you a short idea before I will solve it. So it will be, first you need to represent what does the sum and carry represent, and then you need to check which of the operations can be done parallelly, since it is given that both complemented and uncomplemented values are available at the same time. Then it will be easily solved. So let's start one by one. What is the sum? Sum equals to A XOR B XOR C. Now if like, it will be easy if you can remember it. So I know the formula, then I will write A bar B bar C plus A bar B C bar plus A B bar C bar plus A B C, and the carry is a majority voter A B plus B C plus CA, right? So it is given that both A bar B bar, like A and A bar, also B and B bar, are already present in the circuit as are already present in the sentence. It is given that all inputs are available in both complemented and in uncomplemented form. So you see this one, this one, this one, and this one, which are basically AND operations, can be done in parallel, right? These are 4 independent operations and it can be done in parallel. So it will require one AND. So basically it will require 4 AND parallelly. What does that mean? That means all the 4 operations can be done at the same time. So the delay in this case will be only delta. Next we have, after we get the AND operations, the result of these 4 AND operations, we will just use a OR. To add them up. So that will require another delta. So the total delay is 2 delta. Delta plus delta, 2 delta. Right? So first is we are performing 4 AND operations parallelly, that will require 1 delta. Then the result of the 4 are ORed. So you will require only 1 OR. So that is 1 delta. So there is total 2 delta, that is the time required in the scenario that is given, that is a delay we require. Similarly for carry, these are 3 independent operations, right? So again this can be done parallelly. So 3 and that is 1 delta, and then 1 or that is 1 more delta. So total delay in this case also 2 delta, right? So both for sum and carry, the total delay is 2 delta and 2 delta. So the correct option is A. So correct option is A. So if you have any doubt, you can ask regarding this. So can you explain the value of delta in case of uncomplemented form? It is not, see, it is given both inputs are available in complemented and uncomplemented form. So it won't require another delay. So the delay is only for basic gates OR and XOR. Others it is not required. So that is, you will require only delta plus delta, that is for AND and OR. Okay, so 2 OR, no, it is not 2 OR, because you will require only 1 OR. Like it is not given that how many input the OR or the AND function is. So all the 4 can be OR at the same time. So it will be only 1 OR. So you practically will require 4 AND operations and 1 OR operation for in case of sum, and for carry it will require 3 AND and 1 OR. But the AND operations in both cases are parallel, so you will require only only delta delay. So total delay in both cases are 2 delta and 2 delta. So if you have any doubt, you can ask regarding this. The slides is there. I've uploaded all the slides. You check the link. There is only one Google Drive link. You check the link and you will get the slides there. In that Excel sheet there is a two columns. One is the YouTube links and one is the Drive link. In the Drive link you will find all the slides there. Okay, so the next question is, which of the following statement are true for carry look ahead adders? Addition can be carried out in constant time. All carries can be generated in parallel. The cost of carry look ahead adder increases because rapidly with the increase in the number of bits. So what will be the answer? You can try. So option A, true. Why? Because in carried lookup adders, all the it is the speciality of the carried lookup adders that the additions can be carried out in constant time because all the carries generated are in parallel. It is not in a like a sequential way. It is mostly a parallel way. So option 1 is true. Option B is also true because all the carries generated are parallel. These are the two exclusive features due to which carry look ahead adder are used. Now option C, it says that the cost of carry look ahead circuit increases rapidly with increasing number of bits. This is one of the problem with CLA. So this is true. So if you ask me why, the question is, the simple is, so if you see the carry function, it is given as GI plus PI CI. So if for bits like the first bit, it is quite simplified. Z0 plus P0 C0. Now as the number of bit increases, it becomes really a costly circuit, because in that case C1 will be G1 plus G0 P1 plus C0 P0 P1. Now if it is bit 2, like for if it is 3-bit number, then the third bit carry will be G2, sorry, this will be 1, this will be 2, and this will be 3. G2 plus G1 P2 plus G0 P1 P2 plus C0 P1 P2. So as you see, the number of bits increases, the circuit and of the carry generation is constantly increasing. So that is the one of the most uh, drawback of the carry look ahead adder. So the, the cost will also increase as the number of bits increase. So as a result, the option true is option C is also true. Correct. So this was one of the best basic questions, like theoretical questions. So let's go to the next one. So carry save adder consists of cascaded full adders, independent full adders, parallel adder in the last stage, carry select adders. So what is like carry save adder? If you look at a carry save adder, it will look like this: x0, y0, z0, and it will, this is a full adder, this will generate a C0 and S0, carry and sum, right? Next, for the next bit, again the same case: x1, y1, z1, c1, s1. So if we continue like this, for the nth bit, it will be same. It will be xn, yn, zn, and you will have this cn and sn. So it will be for a n bit carry save adder will have n such small 1 bit full adders, and all the n bits in that case will be independent full adders, and it can be done parallelly. Now what happens? The next stage, in the next stage, all these carry and save are taken as input, and we use a parallel adder for adding all this like all these carry and saves. Right, this is the property of carry save adder. So the correct option in this case will be option B and option C. Right? These are the two options that will be correct. So let's go to the next question. So you have been given a 5-bit carry look ahead adder and suppose the two numbers are A10110 and B10111. So what will be the carry generate and the propagate signals? So what is carry generate and what is carry propagate? So carry generate, that is represented by GI, is basically AI BI, where A and B are in digit numbers. And what is carry propagate? PI is equal to AI XOR BI. Right. So in this case, it has been told. So what will be the carry generate and carry propagate signal for A and B? So it is quite simple. So for the G, we'll simply the number is given us. Sorry, the number is given us A equals to 10110 and B is given us 10111. So to generate G, what we will do? We will just multiply, just add each of the digits, right? So what it will be if we add this? It will be 1. Then the next bit will be 0. If we add 0 and 0, then it will be 1. Then it will be 1, and the end of 0 and 1 is 0. So this is the G signals that will be generated. Now for generating the propagate signal, what we need to do? We need to XOR each of the digits. So what it will be? 1 XOR 1 is 0, 0 XOR 0 is 0, 1 XOR 1 is 0, 0 XOR 1 XOR 1 is 0, and 0 XOR 1 is 1. So this will be the propagate signal. So which of the option is correct? Option C. Any doubt? You can ask if you have any question regarding this. So how do you multiply G and P? We are not multiplying G and P. We are just generating G and P. And it is not multiply, it is AND operation. What we are doing for G and P. So I will again repeat. So what we did. So carry generate is GI is AI BI, that AI and BI, and propagate is basically AI XOR BI. So it is given us, the two numbers are given to us as 10110 and B is 10111. So we need to generate the carry generate and carry propagate signals. So what we will do is, for G, we will just for generating the Z, we will just like and each digit of a and b. So if we and the first digit of a and b, that is 1 and 1 is 1, 0 and 0 is 0, 1 and 1 and 1, 1 and 1 is 1, 0 and 1 is 0. So the generate signal which we get is carry generate signal is 1 0 1 1 0. Next we come to the propagate signal. So the propagate signal, we just XOR the bits. So 1 XOR 1 is, if you look at A and B, 1 XOR 1 is 0, 0 XOR 0 is 0, 1 XOR 1 is 0, 1 XOR 1 is 0, and the last one is 0 XOR 1, that is 1. So the correct answer is option C. So let's go to the next question. So it says we have been given a, suppose we have, it is related to Booth's multiplier. I hope everyone remembers the algorithm that has been discussed in the class. So it is given that we have a Booth's multiplier. We are multiplying minus 9 into 12, where each number is represented in 5 bit. What will be the value of A and Q, that is temporary register and multiplier, after the third step? Okay, so let's start. So step there is A, step 0. What will be the initial values of A? A will be given as 5 bit, 0 0 0 0 0. What will be the Q? Q will be 12, so it will be 0 1 1 0 0. Next is Q minus 1. So Q minus 1 will be initialized as 0, and then there is M. M will be represented by minus 9. Minus 9 in 2's complementary form, it will be 1 0 1 1 1. So minus 9 is basically 9 is given by 1 0 0 1. So if we find the 2's complement of it, it will be 1 0 1 1 0 plus 1, that will be 1 0 1 1 1. So the first operation is initialize. So this will be the initialization portion. So in the step 0, the A is 0, that is the accumulator. The quotient is 0 1 1 0, that is 12. Q minus 1, it will be initialized as 0. And M is 1 0 1 1 1. So what is the next step? So if you remember Boole's algorithm, at each step we check what is the value that is in Q0 and Q minus 1. At each step we check what is the value that is at Q0 and Q minus 1. So what is Q0? This one, and Q minus 1 is this one. So if the value in this case is 0 0, what does 0 0 means? 0 0, if it is 0 0 or 1 1, we do a arithmetic shift right of A Q q minus 1. So let me write it again. ASR A Q minus 1. So since it is 0 0, we will do a basically a arithmetic shift right of q minus 1. This is the step 1. So what will be the value if we shift this one? So basically, if we will consider all these as a single element and we will shift one to the right. So it will be, so this one will be shifted to this one, 0. This 0 will be shifted here. 0. Then the 1 here will be shifted here. 1. This one will be shifted here. 1. This 0 will be shifted here. 0. And this 0 will get shifted here. 0. And here all the 4 other zeros will be shifted. And will be the last one, so it is an arithmetic shift, it will be a 0. Right? And the m will remain as it is. It will remain same all throughout the computation. So this is the first step. Why we did it? Because the value at q0 and q minus 1 is 0 0. So we did an arithmetic shift right of q minus 1. So the next step, the step 2, what we will do, we will again check what is the value stored in q0 q minus 1. What it is? Again 0 0. What we will do? Same arithmetic shift right of a q minus 1. Right? So m will remain same. Let's write out m first. So what will be the value? 0 will be shifted here. 1 will get shifted here. 1 will get shifted here. Then 0 0, and this 0 will be shifted here. This will be the value, and the rest all 4 zeros again will be as it is shifted, and the last one will be again 0. Right? Now step 3. Now it is given that what is the value in q0 q minus 1? It is 1 0. Now if you recall the algorithm, what it will do? It will first do a equals to a minus m in this case. Right? So what it will be? A is equal to a minus m. So what is the value of a? 0. What is the value of m? Minus 9. So what it will be? So we are basically doing, if we note here, 0 minus of minus 9. So basically here we are doing is 0 minus of minus 9. So what it will be? Plus 9. Right? So we'll write down here 9. Else everything remains same. Right? Now the third step is not yet complete. What is the remaining step of third step? It is again same. Arithmetic shift right a q minus 1. So what it will be now? 1 will be shifted here. So m will remain same, sorry. M as always will remain same. 1 will be shifted here. 1 will be shifted here, then there will be 3 zeros. Next this 1 will be shifted here, right? So this will be the value of q. Next let's write down the things which are already present here. 0 0 1 0. What will be the last? The same in case of arithmetic shift, that will be a 0. So this will be the this will also be step 3. Right, so the correct answer is option C. This will be the value of A and Q after the third step. So if you have any doubt, you can ask. You will get the, I mean you will get the slides. If you look at the, if you go to the NPTEL website, you will get the slides like in the for this coursework you will find that live session, and under live session you will get the link of this recording and also the Google Drive where you will find this like PDFs of these solutions which I am doing here. Sir, define 1 second please. Okay, so I will like I will discuss this problem again once again. So this one is quite some that will always be helpful. So it is given we have two numbers -9 and 12, and we are using and we will be using the Boole's multiplier where each number is represented 5 bits. So what will be the value of A and Q after the third step? A is the temporary register, or you can call it as accumulator. Q is the multiplier, which in this case is 12, and M is the multiplicand, which is in this case -9. So -9 for any 2's complement multiplier, like it has to be represented in 2's complement form. So if you find, so if you have like you know how to find out the 2's complement form of 9, so that will be 1 0 1 1 1. I have shown, see in the topmost corner, like how to do it. Like you will just flip the bits and add 1. So that is how we initialize the step 0. Now in the step 1, so what does the Boole's multiplier like show? So it has it always checks these two, Q0 and Q1. What is Q0? This one is Q0 and this one is Q minus 1. Now like you always check in at each step, like what is the value that is stored in these two. So if it is 0 0, if you remember the algorithm, like that is there in the slides that has been shared for week 7, you will find that if it is 0 0, we simply do the arithmetic shift right of A Q Q minus 1. That is, this total set we do a arithmetic shift right, like this total we do a arithmetic shift right. Next what we do is, for the step 1 we check what is the value in 0 0 1. So you do a arithmetic shift right. So what is the arithmetic shift right? This 0 will be shifted here, this 1 will be this 1 will be shifted here. We have done that. This 1 will be shifted here, same. Then 0 will be shifted here, done. And this 0 and this 0 will be shifted here. So that is 0 0 0 1 1 0. And next here the remaining 4 zeros will be shifted here, and the last one, since it's arithmetic shift, we will add a 0. Next, we will again check what is the value stored in Q0 and Q1. It is again 0, 0. So we repeat the same process of just an arithmetic shift of Q minus 1. So we will again shift it. So 0 will come here, right shift, 1 will come here, 1 will come here, 2 zeros will come here, and this 0 will come here, and these the remaining 4 zeros will come here, and 1 extra 0 will come because it is an arithmetic shift, right? Next, what it comes is this. So now here comes is the two Q0 and Q minus 1 is 1, 0. So what is this case? In this case, if you remember the Boole's algorithm, what we do is first do a is equals to a minus m, and then we do a arithmetic shift right. We did the same here. So a equals to a minus m. So what is a in this case? 0. What is m in this case? Minus 9. So what is the operation doing? 0 minus minus 9. So what does it mean? It means 9. So we will rewrite 9 here. Fine. Next, q remains same and 0. Now the next step is again do a arithmetic shift right, a q q q minus 1. What it does, it puts 1 here. It puts the value of q1 becomes now 1. This value this 1 comes here, then 0 0 3 zeros comes here, these 3 zeros comes here, and the last bit comes from here is 1, and then this 4 comes here, and this is the 1 0. So this is how we get the value of a and q. Clear now? So what is the operation in case of 0 1 answer? After step 3 it is 1 0. Yeah, it is after step 3 it is 1 0. So in case of 1 1, so if you this question, you should look at the slides that has been shared for week 7. You will find there that if it is 1 1, it all similar to 0 0, it will do a arithmetic shift right, and do a q minus 1 of arithmetic shift right only. Now if it is let me just draw it once, then it will be easier for you. Q0 q minus 1. The case is 1 0 0 0 1 1. Right, these are the 4 cases. So in case of 1 0, it will be a equals to a minus m. In case of 0 1, it equals to a equals to a plus m, and in case of 0 0, it is just a is a q minus 1. Is a q minus 1. So in all this case, this is the common step. So this ASR step, arithmetic shift right, is always the common one. Else the other 2 cases, if it is 0 1, it will be a equals to a plus m, and if it is 1 0, equals to a minus m. Clear now? This is the algorithm I have repeated. Okay, so let's go to the next question. So the question is, which of the following statement is a true? Boole's multiplier is faster compared to add and shift multiplication approach. Boole's multiplier inspects 2 bits of multiplier at every step. Uh, Arithmetic shift operation is used in Boole's multiplier. So all of them are, the correct option is A is true. So one of the reason it is faster is because of the encoding which is used, that is the Boole's encoding. One of the reason is that is one of the reason that Boole's multiplier is faster compared to just normal shift and add multiplication approach. Number B, Boole's multiplier inspects 2 bit of multiplier every step. I showed like in the working that the two bits which are inspected are Q0 and Q minus 1. These are the only 2 bits that are inspected at each case. And the Boole's multiplier right shift operation is used in Boole's multiplier. That is also true. We use the ASR, Q minus 1 operation at each step. So all of ABC, all of these are true. So let's go to the last question. So suppose we have we are dividing 36 by 6 using a restored division method. So when A and M are like A and M are represented in 4 bits, what will be the value of A after the third step? Again, this was this algorithm was present in this week's lecture, restoring division method. So I will quickly show you the steps that is required. So what happens in each step, that is step A, Q, M, here is the operation. So what is the step 0? Step 0 will initialize the elements. So what is A? A will be the accumulator, that is 0 0 initially. What will be Q? Q will be in this case 37. So what is 37? 37 will be 1 0 0 1 0 1. It is 32 plus 4 plus 1, 37. M will be 6 0 1 1 0. So this will be the initialization. Now step 1. So what happens at each step? We do a shift AQ left and then do it as per the value in the Q0 bit. So what will be the M value initially? 0 1 1 0. We do a shift left AQ. So what does your left shift of AQ does? So it will be 0 0 0. So this one will come 1 here, 0 0 0 1. Now it will be 0 0 1 0 1 0, because it will be always shifted 1 to the left, and the last bit will be 0 as the result. Now we check. Now our next step is this is step 1 continues. The next one is a equals to a minus m. What is a in this case is 1 minus what is m? M in this case is 6. So that will be minus 5. So how to represent minus 5? Minus 5 will be represented as 1 0 1 1. 2's complement form. Q will remain same. And m will remain same. Now if you check what is the main part of the algorithm comes. So at each step it checks what is there in the Q0 bit. So what is there in the Q0 bit? 0. So if Q0 is 0, what it does? It does a equals to a minus m. That is, it restores the value of m to what it was previously. So in this case it is, what is a? A is in this case minus 5. What is m in this case? What is m in this case? 6. So that will be 1. So the value will be 0 0 0 1 0 0 1 0 1 0, and m value will remain same. Right, so this is step 1 completed. So each step will be same. Again we will do a shift left, then we will again minus it and check what is the value of Q0. If the Q0 is 0, we will a is equals to a plus m. If the Q0 is 1, we will not do the step. Right. So now let's come to step 2. Step 2 is value of a will be first what we do is shift left AQ. So we will shift left AQ. So it will be 0 0 1 0. This 0 will come here. Then it will be 0. We are doing the operation shift left. 0 1 0 1. 0 1 0 1 0 and a 0, because the last operand will be 0 in this case whenever we shift left. So it will be 0 1 0 0. Now what we will do, just like previously we will do a equals to a minus m. So what is a in this case? 2. And what is m in this case 6. So 2 minus 6 is minus 4. So what it will be? Minus 4 is 1 1 0 0. It is all 2's complement form. Q will remain same 1 0 1 0 0 0, and m will be just like 1. Now again we will observe what is the value in Q0. What is the value in Q0 in this case? Again 0. Q0 is 0. What we'll do is A is equals to A plus M. A is equals to A plus M. So A is in this case minus 4, and B in this case, M in this case is 6. So it will be 2 minus 4 plus 6 equals to 2. So it will be 0 0 1 0 0 0 sorry 0 1 0 1 0 0 0 1 1 0. So one pattern you look. So if you look at one pattern, if you there is one pattern. See, this one and this one value is same. Again, this one and this one value is same, and that is the reason why it is called restoring division method. See, first we do A equals to A minus M, and A equals to A minus M. What will come is a negative number. Whenever we get a negative number, we restore it to the previous value. So, right. So this is one of the constant pattern that defines this restoring division method. Whenever we get a negative number, we will just restore it to the previous version. So up to step 2 is done. Now let's do the step 3. So what will be the first step in the step 3? Let's do it. It will be little messy now. 3. So what we will do, we will again shift left AQ. So what is the value of AQ at the last step? 0 0 1 0 0 1 1 0 0 1. Right. So we will shift left. So what will it be? So it will come down as 0 1 0 0 1 0 1 0 0 0 0 1 1 0. Similarly, the next step is always subtracting is A equals to A minus M. So what is the value of A now? A is 4 and B is 6, that is minus 2. If we find out the 2's complement form of minus 2, it will be 1 1 1 0. This q part will remain same. The m part will always remain same, right? Now again, what is q0? 0. Since q0 is 0, what we will do? We will distort the part. A is equals to a plus m. So it will be 0 0 1 0 0 1 0 1 0 0 0 1 1 0. So this is the final answer, like the value of a and q after step 3. So value of a after step 3. So what is the answer? Answer is this one. So correct answer is option B. If you look here, okay, so this was the final problem. So if you have any doubt, you can ask regarding this. This is a very complicated part, but for solving this you need to remember the algorithm, like these are the two algorithms which we need to remember for this subject, like the Boole's multiplication algorithm and for the restoration division algorithm. These are very common, this kind of questions, like what will be the value after step 3 4 2, something like that. These are very commonly asked questions. So if you have any doubt, you can ask. So if you don't have any doubt, then we can end the session. This was the last question. So we will meet again next week, same time. Thank you.